Hello everyone, I'm Ian, and today I'm going to present to you our fourth year design project topic, a 3D printable metamaterial lens for terahertz optics. Now, you might be wondering, what is terahertz? Well, it's the region of the electromagnetic spectrum between infrared light and microwaves. It's extremely useful in many applications, such as communications, medical imaging, and security screening, as seen here. This is the TSA's full millimeter body scanner. How terahertz works in this application is it passes through materials but reflects off metal, allowing it to detect a knife or something else malicious carried by a passenger. However, terahertz has the difficulty in that it cannot be easily focused. Current terahertz lenses are shaped like this. They are very thick, which means that they are very lossy. As light passes through this lens, it gets absorbed, meaning that it is low efficiency. Also, terahertz lenses today are very expensive, so we want to bring this cost down. How we're going to make a better lens is by using a metamaterial structure, such as this. How metamaterials work is through phase shift. Imagine if you have two cars, one driving along a road and one along sand. The one driving along the road, after a period of time, will have gone much further. Light behaves in the same way. As it passes through a material, it slows down. So if you have a material like this, you can essentially focus the light with a much thinner lens. So how we designed it was we started with an optimal phase shift right here. As you head radially outwards, you need a bigger phase shift to properly focus the light. So how we adapted this to a lens was by first discretizing our structure into many different cells, about 1.5 millimeters by 1.5 millimeters across each. Then, once the lens was properly discretized, we simulated the device and figured out what phase shift was required at each different cell. Then, once we knew what phase shift was required, we simulated over a pillar structure, like shown here. We adapted the pillar dimensions, making them thinner, fatter, taller, or shorter. By changing the amount of structure present in the pillar, you change the phase shift associated with that particular pillar. This means that we could create a library of pillars, each with an associated different phase shift. Then, we simply took the pillars with the right phase shift and put them into the lens design right here. You can see our optimized algorithm right here. In the middle, you see that the pillars are very small, with a small height and a small radius. This makes sense because a not very big phase shift is required. Then, as you move radially out, the pillars get larger and larger. This makes sense because you need a bigger phase shift at that point. Then, you see that they get smaller right here. This makes sense because you reach the 2 pi phase shift limit, so it sort of overlaps back to 0 since you've gone the full circle. And then when you go outwards, they get bigger again. So this was sort of a secondary confirmation that our lens design made sense. After we 3D printed our lens right here, we implemented it into this system here using vector network analyzers. So here we have a terahertz source that goes through a pinhole to become a point source, where then it passes through our lens in a shape right here. Finally, it hits the terahertz detector right here. How we managed to get our measurements was by moving the terahertz detector across slowly, taking measurements every 4 millimeters in an XY pattern. By doing that, we managed to determine the power output after it had been focused at each point. The result is the two graphs shown here. On the left here, we have a graph at 80 gigahertz. We see that the focal point is quite good, with a spot size of about 1 centimeter by 1 centimeter. Considering that the lens was originally 5 centimeters by 5 centimeters, this represents a marked improvement over the original terahertz radiation. On the right here, we have 90 gigahertz. The spot size is a bit bigger here, at 1 centimeter by 2 centimeters. This is because the difference between 80 and 90 gigahertz changes the phase shift, meaning that the resulting focusing is quite a bit different. So here we have some of the simulations we took when designing our lens. Right here is the pillar that we are simulating, and this is the terahertz light passing through. You see that the electromagnetic waves in their phase are changing as they pass through. You can also see this effect right here. Our next steps in this project would be to fully verify our evaluation procedure and to also implement it in some of the devices. One way that we could possibly implement this into our application right here is by stacking the lenses in a manner like this. This means that you can have very low losses due to how thin the lenses are, but still get very good focusing with multiple lenses. So instead of using a giant machine like this, you could have a small terahertz camera to look at an entire crowd. This means that you don't need one by one, and the whole process is much less annoying for everyone, while still maintaining high security for the airport. Another potential application, if the 3D printing could be good enough with a sufficient resolution is to move to the optical range. Unfortunately, this is not currently viable since 3D printing technology does not have sufficient resolution yet. Before I end, I would like to thank our two consultants. The first, Dr. Baishi. He was the one who helped us with the whole printing procedure and helped us also design our lens. Our second consultant was Dr. Safa Vinayani, who helped us do the characterization shown here, and his grad student, Dr. Hadi.